Hello everyone, I'm Nitinja. This is my presentation for 2024 CT. My study is about effect of noise and topology on multiphoton quantum protocols. Multiphoton quantum protocol means that if you're trying to send a logical message across a quantum network, you encode each of the logical bits into multiple qubits. So for this study, the protocol that we chose is known as three-stage protocol proposed by Dr. Subhash Kak in 2006. The protocol goes as follows. You have Alice, the sender, the Bob, the receiver. Alice encodes all of the logical bits into multiple qubits in a basis of common knowledge, let's say Z basis, then applies a rotation to all of these bases, and this rotation is only known to Alice. We call this operation as unitary A. Sends these updated bits to Bob. Bob applies a similar rotation, but the angle is only known to Bob this time. We call that unitary operation UB, sends these updated bits back to Alice. Alice removes her original rotation, sends the bits back to Bob. Bob removes his rotation and gets the original qubits back, measures them in the basis of public knowledge, and gets the message uh, securely. Okay, yeah. So the beauty is that the unitary operation UA and UB in fact commute because they are rotation matrices, and you can do the maths and well it commutes. So that way, at the end of the protocol, Bob gets back the original bits. Okay, so now the method is basically simple. How we conducted the study, we created the logic bit string of 128 bits or 96 bits in some cases, applied the protocol was followed. Then in between the protocol, each and every node has noise models like bit flip, phase flip, amplitude damping, and collective rotation. Collective rotation rotates all the bits by a random angle. Bit flip changes from 0 to 1, 1 to 0. Phase flip takes 1 to -1, and amplitude damping takes all the ones gradually to 0 or a mixed state. Yeah, so these were applied. We looked over torus, grid, direct, and ring topology. In the graphs, you can see that the y-axis says the successful bits per qubits per bit. That means if you send 100 qubits for one bit, how many of them were in the same state at the end of the protocol in the presence of noise? And we can see that well more than like roughly about 50% were there in the heavy noise situation. All in the first graph, all of the errors were applied with a probability in between 15 to 30% each. And yeah, the second graph shows the attenuation error. Basically, transporting over the optical cable can cause loss of qubits, and we can see that for some of the topologies, the loss is higher. So this gives us a good estimate about how and where we want to design our network and how to which topology is better. Feel free to reach out to me on LinkedIn, and you can always go over my full paper. And if you have any question, you can drop me an email. Thank you.